we take up another class of second order linear differential equations. This class is called Cauchy-Euler equations. They are of the type x square y double prime plus ax y prime plus by equal to 0, where b and a are real numbers. Here we assume that x is greater than 0. To find a solution of this kind of differential equations, we substitute y is equal to x raised to m. On substituting y is equal to x raised to m in this equation, when we take double derivative of x raised to m, we get m into m minus 1 times x raised to m minus 1 that we put here. When we take single derivative of x raised to m, we get m x raised to m minus 1 that we put here. So the equation will transform to this. Here we have also substituted y is equal to x raised to m. So this equation get transformed into this when we substitute for y x raised to m. Now since x is greater than 0 and here we get xm common, we can cancel xm because xm is not equal to 0. We end up in getting this quadratic equation in m. Rearranging the terms, we get m square plus a minus 1 bracket times m plus b is equal to 0. This is called auxiliary equation of a given Cauchy-Euler equation. On solving this quadratic equation in terms of m, we get two values of m, namely bracket 1 minus a bracket close plus minus square root of a minus 1 whole square minus 4b whole divided by 2. So the two values are denoted by m1 and m2. These are two roots of the given quadratic equation, which is the auxiliary equation of the given Cauchy-Euler equation. Now, just like in the previous case, here also we consider the various cases and corresponding to those, what is the corresponding solution for the Cauchy-Euler differential equation. First case, when the roots are distinct and the roots are real. That means the m1 and m2 are real numbers and they are distinct. In that case, are x raised to m1 and x raised to m2 linearly independent? So we take the ratio of x raised to m1 and x raised to m2, that is x raised to m1 divided by x raised to m2, that is x raised to m1 minus m2, and that quantity is not a constant quantity. Hence, they are linearly independent. So, what will be the general solution? That will be the linear combination of these two linearly independent solutions. So, the general solution will be y is equal to c1 times x raised to m1 plus c2 times x raised to m2, where c1 and c2 are real numbers. Now consider the second case when the roots of this quadratic equation are real and equal. In that case, the quantity under the square root will have value 0, that is a minus 1 whole square minus 4b will be equal to 0. So, the equal roots will be 1 minus a divided by 2. So, from this we get only one solution of the Cauchy-Euler equation, namely y is equal to fx is equal to x raised to 1 minus a divided by 2. This will be solution of the Cauchy-Euler equation. But we want to find another solution such that the two solutions, this one and the other one, are linearly independent. So to get such a solution, we take the help of reduction of order that we have learned before. So in that case, first we determine what is the px of the given Cauchy-Euler equation. So for that we have to write the given Cauchy-Euler equation in standard form. In order to write the Cauchy-Euler equation in the standard form, we have to divide the entire Cauchy-Euler equation by x square. So it will look like y double prime plus a divided by x y prime plus b divided by x square y is equal to 0. That is what we have written here. Y double prime plus a by x y prime plus b divided by x square y is equal to 0. This we obtained from the Cauchy-Euler equation by dividing the equation by x square. This is in the standard form. From this we get px to be equal to a by x. In order to get another solution, gx, whether gx is linearly independent from fx, we have to set gx to be equal to vx times fx, and we have to determine the vx. We know the formula for vx from our previous theory that we have developed. So vx is equal to integration of e raised to minus integration px dx divided by y1 square dx. Here we substitute for px a by x, and for y1 we substitute x raised to 1 minus a by 2. So this is what we get. So we are computing the integration of e raised to minus integration of a by x dx divided by x raised to 1 minus a dx. So in the numerator we have e raised to minus a log mod x. So that will be e raised to log mod 1 by x raised to a. That is, in the numerator we will have 1 by mod of x raised to a. Since x is greater than 0, so in the numerator we have 1 by x raised to a. So this together with the denominator gives us 1 by x. So integration of dx by x is equal to ln of x. So we have determined that Vx is equal to ln of x. We are not writing the integration constant. We don't need it for computing Vx. So we multiply Vx with fx to get Gx, and Gx is equal to ln of x bracket times x raised to 1 minus a divided by 2. So fx and Gx are linearly independent solutions of the Cauchy-Euler equation when the auxiliary equation has equal real roots. So in that case, the general solution will be y is equal to c1 times fx plus c2 times gx, that is c1 times x raised to 1 minus a divided by 2 plus c2 times x raised to 1 minus a divided by 2 ln x, where c1 and c2 are real numbers. Now we consider the third case where the roots of the auxiliary equation are complex. Let the roots be m1 equal to mu plus iota nu and m2 equal to mu minus iota nu. So x raised to m1 will be equal to x raised to mu times e raised to iota nu log x. What we do is, because x raised to m1 is equal to x raised to mu times x raised to iota nu, that x raised to iota nu we wrote it as e of log of x raised to iota nu, and iota nu from power we brought in the front and multiplied ln x with iota nu, and we obtain this quantity. So this is equal to x raised to mu bracket cos of in bracket nu ln x bracket close plus iota sine bracket nu ln x bracket close, and the other bracket also close. This we obtained using the Euler identity. Similarly, x raised to m2 will give us x raised to mu times e raised to minus iota nu ln x, which is equal to x raised to mu bracket cos bracket nu ln x bracket close minus iota sine bracket nu ln x and two brackets closed. Again here the solutions are complex valued functions, and we want the solutions to be real valued functions. So we will obtain real valued functions from these two. The trick is the same. You add these two solutions and then divide by 2. On adding these two solutions, these two will cancel. So we will have 2 times x raised to mu cos nu ln x and bracket close, and when you divide x raised to m1 plus x raised to m2 by 2, you get mu cos nu ln x. Nu ln x was in bracket, so that is one real valued solution that you obtain, and another solution so that they together are linearly independent. Such a solution you can obtain by considering x raised to m1 minus x raised to m2 divided by 2 iota, and that will give you x raised to mu times sine in bracket nu ln x. So these two linearly independent solution. So for the general solution, you take linear combination of these two solutions and you obtain this general solution. Namely, general solution is y is equal to x raised to mu in bracket c1 cos in bracket nu ln x bracket close plus c2 sin bracket nu ln x, two brackets closed, where c1 and c2 are real numbers. So these were the three cases that arise in the Cauchy-Euler case, and you can clearly see that these two solutions are linearly independent because the ratio of the two solutions, namely the y1 part here and the y2 part here, is tan of nu ln x, which is not constant. Now here are some examples based on what we have learned. These examples are of Cauchy-Euler equations. We'll try to solve them. You can pause the video and solve these three questions. You can verify your solutions with the one that is given here. We covered all the three cases in these three examples, namely when the roots of the auxiliary equations are real and distinct, and the roots of the auxiliary equations are real and equal, and the third case where the roots of the auxiliary equations are complex. Next we study non-homogeneous second order linear ODEs. Consider the non-homogeneous differential equation y double prime plus px y prime plus qx y is equal to rx. This is called non-homogeneous because rx is not equal to 0. Here px, qx and rx are assumed to be continuous functions on an interval I. The solution of this non-homogeneous equation, differential equation, is associated to the associated homogeneous differential equation, namely y double prime plus px y prime plus qx y is equal to 0. how are the two solutions related? That means how are the solution of the non-homogeneous equation and the homogeneous equation related? Here we see the result which gives us the relation between the non-homogeneous ODE and its associated homogeneous part. Suppose Yp is any solution of the non-homogeneous second order linear ODE, namely y double prime plus px y prime plus qx y is equal to rx, where px, qx and rx are assumed to be continuous function of x, and let y1 and y2 be a basis of solution space of the corresponding homogeneous differential equation, that is y double prime plus px y prime plus qx y is equal to 0. Then the set of solutions of the non-homogeneous D is given by the set of C1 Y1 x plus C2 Y2 x plus YPX such that C1 C2 belongs to R. What does it say? Suppose you have homogeneous differential equation associated, namely y double prime plus px y prime plus qx y, having y1 and y2 as two linearly independent solutions. Then what is the general solution of the homogeneous differential equation? C1 y1 plus C2 y2. So how do you get the solution of the non-homogeneous ODE? If you know one particular solution of the non-homogeneous differential equation, then just add that to the general solution of the homogeneous ODE, and that will give you any arbitrary solution of the non-homogeneous ODE. This says any solution of the non-homogeneous differential equation looks like this: C1y1x plus C2y2x plus ypx, where C1 C2 belongs to real number. This is a general solution of the non-homogeneous ODE. We will see the proof of this theorem. So let Ly be defined as y double prime plus px y prime plus qx y, and let phi x be a solution of Ly is equal to Rx. What is Ly is equal to Rx? This is nothing but the non-homogeneous differential equation, a way of writing a non-homogeneous equation in a shorter way. Then we compute L of phi x minus ypx. Since x is a linear operator, we can separate it as L of bracket phi x minus L of ypx. We know L of phi x is Rx because phi x is a solution of Ly is equal to Rx, and we know yp is also a particular solution of the non-homogeneous ODE. So L of ypx will also be Rx. So Rx minus Rx is 0. This means that L of phi x minus ypx is equal to 0. So phi x minus ypx is a solution of the homogeneous ODE. But we know any solution of the homogeneous ODE can be written as C1 y1x plus C2 y2x. So we can write like this for some C1 C2 belonging to R. If we rearrange, we get phi x is equal to C1 y1x plus C2 y2x plus ypx by transferring this on the other side. Thus, this means that the general solution of the non-homogeneous ODE is of the type C1 y1 plus C2 y2 plus yp, as claimed in the theorem. What is the summary? The summary is that we get a method of finding the general solution of the non-homogeneous ODE. For that, what do you have to do? First, we get the general solution of the corresponding homogeneous ODE. That is the associated homogeneous ODE for every non-homogeneous ODE. We find the general solution of that. That is, we find the two linearly independent solutions. Then we write C1 y1 plus C2 y2, where y1 y2 are the linearly independent solution of the homogeneous ODE. And then we try to compute somehow a particular solution of the non-homogeneous ODE. Then the sum of the two, the general solution and the general solution of the homogeneous ODE and the particular solution of the non-homogeneous ODE, that will give us the general solution of the non-homogeneous ODE.